Welcome back to our continuing series on analytic trigonometry. That is where we're using identities and algebra techniques like factoring and simplification to simplify trigonometric equations and identities and expressions. And what we're going to do today in this set is we are going to start adding on a ridiculous amount of other formulas to our repertoire. Remember, we have Pythagorean identities, cofunction identities, sum and difference formulas, and going forward we're going to add on even more. First, in this video, we're going to look at adding on double angle and half angle formulas. In the next, we're just going to throw even more into the mix. And then finally, we will start using those identities to prove things. So let's get going here. Suppose I've got some known theta. Well, it's given, right? And it's given such that sine of theta is 4 over 5. And I want to know what sine of 2 theta is. Well, I can't just say, well, it's 2 sine theta, right? The 2 doesn't just move outside of an argument of sine in the same way that, it's not multiplication. You can't just multiply in whatever order you want, because this is not multiplication. As evidenced by the fact that, well, if I had 2 sine theta, that would be 8 over 5. That's more than 1. That's more than what sine can possibly be. So, with that not at our disposal, maybe we'd bust out a calculator, find the arc sine of 4 over 5, which is 53.1 degrees, give or take. But we can't just double this and put that into a calculator and find the sine of 106.2 degrees, because that's not what I want either. Right? I know theta's in the second quadrant, this value's in the first quadrant. So to find my actual value for theta, I would have to subtract it out of 180. That would be theta. 126.9 degrees. So if I were using a calculator for this, I could double that, find the sine of 253.8, and I would get out about 0.9603. Well, great. Except not really, right? This is inexact. It could be a lot better, and I wanted to make it be better. So, to exactly find the sine of 2 theta, I'm going to need a little more. And that little more is going to come from the sum and difference formulas. Right? Sine of 2x is just sine of x plus x. So sine of 2 theta would be sine of theta plus theta. Applying our sum formula from last time, that's sine cosine plus cosine sine, but since it's x all the way through, you've got sine cosine, sine cosine, you have 2 sine x cosine x. So skipping down, sine of 2 theta is going to be 2 sine theta cosine theta. Well, what is cosine theta here? Well, recognizing I was in the second quadrant, right? I had this as my triangle. I had a hypotenuse of 5. Getting there. Opposite of 4. Right, and here was theta. Out here to get into this place. Wow, that's terrible. I'm sorry. But anyway, we're in the second quadrant. Hypotenuse is 5. Opposite is 4. So necessarily this adjacent side needs to be negative 3. So that's how I got cosine of theta to be negative 3. And so putting that all together, I've got 8 over 5 times negative 3 over 5, negative 24 over 25, which in decimal form is exactly 0.96. So that extra 3 10,000ths is not actually part of what sine of 2 theta is exactly. Now, of course, all this was contingent on having theta being in the second quadrant. Why don't you go ahead and tell me exactly what sine of 2 theta would be if sine of theta was in the first quadrant and sine of theta was 4 over 5. So instead of being in the second quadrant, if it were in the first quadrant, what would sine of 2 theta be? I'm going to assume you said the right thing. Going to assume you said positive 24 over 25, because that would be ideal. But moving on. So not only can I make the sine of 2x the double angle formula for sine, I can also do it for tangent and cosine, using the exact same technique. Tangent of x plus x will get me 2 tangent of x over 1 minus tangent squared of x. And then cosine of x plus x actually has a few ways it can go down, right? I've got cosine, cosine, sine, sine, so I've got cosine squared minus sine squared. But using the Pythagorean identities, right, using the fact that 1 minus sine squared, I'm really bad at using my mouse, right, recognizing that 1 minus sine squared is cosine squared, I can make that substitution. And so the second line there gives me 1 minus 2 sine squared of x. And the third line gives me, if I had done it 1 minus cosine squared in for sine squared, I would get 2 cosine squared x minus 1. So there's a few ways it can go. And it's actually going to be the case that these are going to be very useful for what's going to come next, the half-angle formulas. See, now we can double our angle theta and be able to find our new trig functions no problem. What if we went the other way around? What if I wanted to find the exact value of cosine of 7.5 degrees? And I bring that up because we had been able to find cosine of 15 degrees previously, right? 15 degrees was using the sum or difference formulas from last time. But now I want to cut that in half. Can I do that? And the way I would go about doing it is I would start with these over here. Cosine of 2x equaling these guys right here. So cosine of 2x is 1 minus 2 sine squared, or 2 cosine squared minus 1. So I write this here, right? Sine squared, after a little bit of rewriting, sine squared is 1 minus cosine of 2x over 2. Cosine squared is 1 plus cosine of 2x over 2. And if you really wanted, you can get tangent of 2x in a similar fashion. And what we're going to use with this is the fact that, well, I've got double here and half here. So why don't I write 2x as u and x as u halves, right? Make this substitution. So I've got sine squared of u halves equaling 1 minus cosine u over 2. And I take the square root of that, I'm going to get 1 minus cosine u over 2 all in a square root. And it's going to be plus or minus, where the plus or minus is depending on what quadrant u over 2 is in. Right? If u over 2 is in the first quadrant, sine's positive, cosine's positive. If it's in the third quadrant, sine's negative, cosine's negative, second quadrant, fourth quadrant, and so on. Right? And cosine is made the same way, right? I've got the cosine formula, take the square root of this thing, and that's going to get me plus or minus root 1 plus cosine u over 2. And so I'll get to tangent here in a bit. But what I can do now is I can find the cosine of 7.5 degrees, right? 7.5 is in the first quadrant, so I'm going to use the positive square root of 1 plus cosine of 15 degrees over 2. And remembering from last time, or you can check yourself again, cosine of 15 degrees is root 2 plus root 6 over 4. So add that to 1, I've got 4 plus root 2 plus root 6 all over 4, and that comes down to be 4 plus root 2 plus root 6 plus 8, all inside a square root, all positive. And that is the exact value of cosine of 7.5. You can check via calculator to see what the decimal version of this is and what the decimal version of this is, and you should get, accounting for rounding error, pretty much the same number. Alright. And just out of curiosity, what would be the sine of 7.5 degrees? We'll end on that. Coming in next time, we will look at making the half angle for tangent, making a whole bunch of other formulas, in fact, and then just seeing what we can do with that. So I'll see you then.